All right, so we're going to look at molar volume and Avogadro's hypothesis today. So the Avogadro's hypothesis is that if you have two different gases, but they're at the same temperature and pressure, they're going to contain equal numbers of particles. And skipping ahead to the molar volume thing a little bit, that's what's related here. Let's say that you had 22.4 liters of oxygen, and you had 22.4 liters of nitrogen. Those would contain the same number of particles. In fact, how many particles would that contain? If we say 1 mole, Avogadro's number, that's right. So 6.02 times 10 to the 23rd particles of the gas. Let's see. Volume of gases are much more affected by changes in temperature and pressure than other states of matter. So we have to measure them at a standard temperature and pressure. For this unit, pretty much all of the conversions you do will be at standard temperature and pressure. A little bit later on, I'm going to teach you how to handle conversions and calculations with gases that are not at standard temperature and pressure. But that's going to be in a future unit. That's not in this one. All right, so the thing that we're adding to our mole map now is 1 mole equals 22.4 liters. So that's the molar volume of any gas at standard temperature and pressure. And this is going to give you a way to figure out, well, where am I at and what am I converting to? So, for example, if I'm going from mass to volume, how many steps will that take? It'll take 2 steps. What if they just gave me moles and I had to go to gas volume? 1 step. And it also will kind of show you what conversions you need to use. Now, 2 of these conversions are the same every time you use them. That would be the molar volume and the Avogadro's number conversions. Those are the same every time. The one that can change is the molar mass one, because the molar mass depends on the what of the elements in the formula for that compound. So you have to add them up from the periodic table. All right, so let's go over here and we'll work out a few examples. Example 5 here. What is the volume of 219 grams of SO2 gas at standard temperature and pressure? So list off our unknown here. We are looking for volume. And they tell us 219 grams. All right, so we're going to look at the mole map and come up with our plan. Where are we starting at for this problem? Where are we starting at? We're starting at mass. And where are we going to? And to get a final answer, they ask us what is the volume, so we need to go to volume. So it's going to take us 2 steps to get there. So our first step in the plan, we're going to have to do 1 mole equals the molar mass. Add that up from the periodic table. Why did I put a plus sign there? Oh my. All right. So SO2, sulfur is 32.07 or something. Oh, so yeah, we'll go 32.07. And then 2 oxygens, 2 times 16.00. So we're going to be somewhere around 64.07. Yep. All right. And then what conversion will we use to get to volume? 1 mole equals 22.4 liters. We're using molar volume. By the way, they did tell us that. Some of you will read these problems and forget about the standard temperature and pressure thing. The only reason why they tell you standard temperature and pressure is so that you know that it is okay for you to use this conversion. If you're not told that, it's not okay to use that conversion. And I think there's a couple of practice problems that I may have somewhere where it doesn't say that. So if you're not sure, ask me and I'll clarify that for you. All right, so let's set it up. Let's solve. Start with the known, 219 grams of SO2. All right. We're using molar mass. Where does the 64.07 grams go? Top or bottom? It's going to go on the bottom. 1 mole. Yeah, if you need a calculator, feel free to get up and grab one. All right, so numerator and denominator, the grams of sulfur dioxide cancel out. But we're still not to volume yet, so we'll have to use this other conversion that we're given. So this one we used here. This one we'll use over here. This time, moles of sulfur dioxide need to go on the bottom. Oh my, that's a 2. And 22.4 liters. All right, that'll cancel out the moles of SO2 and leave us with liters, which is good because we were looking for volume, and liters is a unit of volume. So calculators, 219 times 22.4 divided by 64.07. 76.5? 76.6.
76.56.
Okay, so 76.6 if we go to 3 significant figures. All right, for comparison, let's look at the mole box for a second and we'll see how big that would be. All right, let's carry on with example 6 here. This time it's asking us what is the mass of 2.17 liters of nitrogen gas. We don't know the mass. You're correct. How does this one compare to the last problem? It's the opposite. We're going in the opposite order. So the conversion factors will appear in the opposite order, and they'll be what?
Reversed.
Reversed or flipped over. Yeah, sure thing. So let's go for it. Don't know the mass. Okay, do know the volume, 2.17 liters. All right, and the plan. So we are currently at volume. So our first step is going to be to use molar volume to go back to the mole. And then our second step is once we're at moles, we're going to use molar mass to go back to the mass. All right, quick math. What's the molar mass of nitrogen? Yes. Simple molecules are nice, right? And you get like the lead-3 chlorate or something, and you're adding up all those things. You're like, why am I doing this? Okay. Yes.
Anytime you do nitrogen or something like that, do you always have to put 2?
Yeah, if it's nitrogen, if they say nitrogen, then the formula is going to be N2. The only time that it would be an individual nitrogen atom is if they specify it's a nitrogen atom, because that's how nitrogen as an element is going to exist. It bonds to itself and makes N2 molecules. It would be like that with the 7 diatomic elements that y'all had to memorize. Yeah, all the other ones will exist by themselves. Like iron would just be Fe, and argon would be Ar. But if you got one of those diatomic elements, you need to write it as whatever the element is with the 2 after it. All right, and that's a good question. Thank you for asking that. Let's see. So let's start out with the known, 2.17 N2. What goes on the bottom? 22.4 liters. All right, so far we have canceled out the liters. We're at moles now. We want to go to grams. What goes on the bottom of the next conversion factor? Yep, we're going to do the moles on the bottom. That's 28.0 grams. 2 point, 2 point what? 2.7 what? 2.71. Great. All right, I show the moles canceling out there. We're left over with grams, so whatever unit is left over here is the unit that our final answer gets. And I've been a little bit forgetful here, and I forgot to box in my answers. I'll box those in so you can tell, hey, that's the answer. This one, grade this. All right. All right, last problem here. Maybe we can get this in the time we have remaining. How many molecules of carbon dioxide would be found in 3.175 liters of the gas at standard temperature? And that's crazy. We started at 2.17 and we got 2.71. Yeah. Anyways, let's look at the mole map for a moment. Where are we starting at with that problem? We're starting with the liters. Where are we going? Molecules down here. How many steps will it take us to get there? Take us 2. Do we need to add up the molar mass? No, because the only time we need molar mass is if we go from moles to mass. So this is nice. We don't have to do that molar mass thing. This one, just 2 steps and use the numbers provided. All right. Unknown, we're going to molecules of carbon dioxide. We know that there's 3.175 liters of carbon dioxide. The plan, so first step to get away from liters. What is this thing called again? 1 mole equals 22.4 liters. Molar volume. We're going to use molar volume. Mole equals 22.4 liters. And then to get from moles to particles, we use Avogadro's number. All right. The solve. So we'll start with the known, 3.175 liters of carbon dioxide. And what goes on the bottom? 22.4 liters equals 1 mole. And then liters of carbon dioxide cancel out. What goes on the bottom of the next one? Moles. I'll figure that out, right? Whatever's here, we can put on the bottom of the next one. Right. Not necessarily the same number, but the unit. So 1 mole CO2, and that's equal to, we're going to molecules. Yep. Again, MCLS is an acceptable abbreviation in my class for molecules. (8.5). Give me let's go 4 significant figures since we had 4 there. 8.532. Thank you. I need a power on that, don't I? E to the 22, yeah. All right. Oh, with 10 seconds to spare.